Okay, why don't we begin? And needless to say, we have a lecture on fun with reading comprehension by Marc Light.
Okay, so we're the reading comprehension group. And we're made up of Pranav Anand at Harvard, Breck at MITRE, Brianne Brown at Bryn Mawr, myself at MITRE, Gideon Mann at Hopkins.
You need a microphone.
Oh, I'm sorry, I forgot.
Let's see.
Okay. Start again, kid.
So this is the reading comprehension group. As I just mentioned, we're made up of Pranav, Eric, myself, Brianne, Gideon Mann at Hopkins, Riloff at the University of Utah, Rooth at the University of Stuttgart. He's actually going to be going to Cornell University soon, and Michael Thelen of University of Utah. So the way we're going to do this is I'm going to talk for around 15 minutes, giving you some introduction, some general results. And then Eric is going to talk about the evaluation metrics, which I'm actually using in some of those results, and also go into some more detailed results. So we're going to give sort of the punchline in the beginning, since we know everyone is tired. And then we'll go into the question analysis, exactly how the system runs. So we'll have the question analysis, the passage taggers, syntax, the candidate ranking, and the alternative architecture. Proposal, which Gideon Mann is going to be making. That's going to be our proposal for future work, the grad student future work competition. Then we'll have our coffee break. And finally, I'll give a couple of slides to jumpstart the discussion and questions. Okay, so let's go ahead and start. So what are these exams that we're trying to do? What is this reading comprehension thing? There are exams like this. You have a passage. In this case, it's a newswire-like passage. And then you have a set of questions at the bottom, which you're supposed to be able to answer based on reading that passage. And your job then, and the system's job, is to read these questions and try to figure out what the answer is, find it. So if you ask the question, when did the mission controllers lose hope of communicating with the lander? You go and you read in there, and maybe one thing you'll do is you look for dates. In fact, that there's a date there at a.m. Monday, which does in fact answer the question, and then you would write that down in a short form. So this is not multiple choice, although we could work on those sorts of things. We're working on these short answer exams. Okay, and we know that the answer is in this passage. Now, these exams, the test set, and all the results most results we'll be talking about, comes from the CBC website for kids. And CBC is Canadian Broadcast Corporation, and we pull down these stories. There's a story each day, and they've been doing this for about 2 years. And then we wrote questions, and not us. A coworker at MITRE, who's not on the development team, Lisa Farrow, and also Tim Bevins, wrote questions on that corresponded to the passages. And she worked for ETS previously, so she has some experience with exactly how that community writes reading comprehension exams. And we have 250 stories in all. So that's around, and there's around 8 or 9, almost 10 questions per story. So we're looking at 2,500 questions. That's what we're working with. We had 75 in our training set, and then 75 in our dev test, and 100 in our final test. So that's to give you an idea of the amount of data that we're working with here. All right. Okay, so why do this? Well, there are many reasons. I've got a couple here. One is that we think it's a good evaluation for natural language understanding technology. And here are some reasons why. One is that you're able to automate the evaluation. And this is, of course, true for multiple choice. But in fact, for short answer, we've done some work previous to the workshop and some more work that we'll talk about here on automating the evaluation of these things. And of course, that's important for system building and also for reproducible results. It's theory independent. One of the difficult things if you're going to evaluate a natural language understanding system is to develop an evaluation where everyone agrees to partake, regardless of whether or not they think syntax is important or whether or not they think that you should do logic in some sort if they're a Shankian, or if they believe in scripts or frames or whatever they believe in. And this has been a problem in the past, and something that the nice thing about one thing that's nice about reading comprehension is that, look, we don't care how you understand this text, just answer the questions. It's tractable but not trivial, and we've done some previous work coming up to the workshop on showing that we certainly do much better than chance using relatively simple methods. But however, you certainly are not in the 90s, and we'll be seeing that quite clearly in the upcoming slides. It provides an impetus for useful and interesting research, more specifically into human language technology. And what we found is that if you understand if you do linguistic processing, your score goes up. These reading comprehension exams, this evaluation, it provides a context in which to explore machine reading comprehension. That's certainly obvious. You can also look at human reading comprehension by comparison, and then you can talk about the combination of the two there. And I'm going to get into a little bit about some applications that you can do if you're trying to help people learn foreign languages, if you're trying to help children learn to read, things of this sort. So you can get into these kinds of applications if you're working on this reading comprehension exams. And so there are both direct and indirect applications of such systems. Certainly, we also believe that if you build technologies that can do well, that help reading comprehension, these technologies are going to be useful for all sorts of different human language technology tasks. Okay, so now if you're a system builder and someone says build a reading comprehension, a system that can take reading comprehension exams, what do you have to do? Well, some of the research questions are, what information does the system need to extract from the question and passage in order to identify an answer? So if you could have any kind of information you want, what would you take in order to answer these things? What do you need? How are you going to get this stuff? So what's even practical? What on that wish list can you actually get? How can you incorporate these different types of information? So even if you have them, you need some way of putting them together in order to actually build a system. And in addition, what are the sort of general knowledge do you need other than what's in the passage specifically and in the question? What sort of outside linguistic knowledge or perhaps world knowledge do you need to do this? Because maybe you need so much world knowledge, we don't think this is true, but maybe if you did, that would be a possible finding, then of course one would need to really focus on that. So the hypothesis for the workshop, and this is on the system building side of things. The hypothesis is that if we have a confederacy of shallow semantic taggers armed with a question analyzer and context question similarity measure, we can pass these CBC tests. So what does that mean? It's sort of flowery. I was inspired when I wrote that sentence, I guess. So the idea is you have this question, and you need to, we think if you have an analyzer that is able to figure out, well, look, this is looking for a time expression, because this one's quite easy. It starts with a when, it's quite likely to be a time. If you had a what, there are different ways of phrasing this that would make it more or less difficult to figure out that this is looking for a temporal expression as an answer. And then we also, perhaps the analyzer will be able to figure out, well, this is a relatively important word with respect to the answer. And then our shallow semantic taggers run off and try to underline all the temporal expressions. So December 3rd, at that time, minutes before beginning its descent, 8 a.m. Monday. And then if we have a co-reference module that takes these things and says, oh, December 3rd and at that time, they're the same. That refers to the same time. So lump those together. Okay, and then once we have these things all tagged up, we can come up with a set of candidate answers. And what we do here is we go through each sentence looking for things of the right type, and then build a candidate for that, and save away the bits of context and the information about the particular type and the context that it's seen into a vector of features that are going to be indicative of correctness. They're going to help us decide which one is the right answer as opposed to spurious ones. Okay. So, and we'll lump together things that are co-ref. So we have December and at is one candidate. Another candidate is this minutes phrase here. And then we have the 8 a.m. candidate here. Once we have these candidates, we can now try to rank them. And we make use of these features. that we've extracted from the context and that are true of the item itself, and hopefully we rank the right answer first. So this is the setup, and our hypothesis is this is going to be enough to get us in the 60s, sort of a D. So what information is Spot utilizing to do this? Well, we have syntactic and lexical information relevant to assigning the question one of 34 primitive semantic types. So we have semantic types like temporal expression, location, money phrase, these kinds of things. We have 34 of them. And we use syntactic and lexical information in the question, local syntactic information, in order to assign this thing, the question to one of these types. Then we have these passage taggers that I mentioned, and they also use syntactic and lexical information in order to find these things of this type in the passage. And finally, we have, again, using syntactic and lexical information relevant to the weighting of terms in the context question overlap. So we have a lot of features that have to do with how well the question and the context are related with one another in order to try to rank the question, the context to bring the proper candidate to the front of the list. So that's what we'll be handing back and hopefully get the right answer. So this is quite primitive in some way. We started with a relatively IR-like approach. Not that IR is primitive, but this sort of term-based word thing, and to look at doing that task that way first. And we did build in some syntactic information. Okay. So what's the context for the hypothesis? The hypothesis being that we can actually pass a test using this type of system. Well, if you do bag of words, and Remedia is another test set that we worked with. I just wanted to give another test set that we worked with in previous years at MITRE. Give some scores. And bag of words is simply saying, look, just take the words in the sentence, see which words in the passage, which sentence has a big overlap with the words in the question, and hand back that sentence. So it's simply IR taking the question as a query and the sentences, each sentence as a document. So just hand back the sentence that has the highest score. And we did a very primitive bag of words. We did some stemming and some stopping, but we didn't do any kind of weighting. So it was just the one that had the largest overlap. And you get 5% on the CBC training, and you get 4% on Remedia. And Eric's going to talk about what these, for now, these numbers mean correct. A teacher would have marked it as correct. And defining what correct is non-trivial, and Eric will be talking about that. Spot 00, which is the system that we started with at the beginning of the workshop, had far fewer types, far fewer taggers, a far less complicated, complex question analyzer, and a very simple ranking algorithm. Got 24 on Remedia and 21 on CBC training data. Okay, so that's where we started. That's our baseline. So how does Spot run? The name of our system is Spot. Actually, I guess you saw that with the Spot 00 already. Here are some results. We have, as I mentioned, the bag of words and the 00. These are the same results as before, except for the fact that we have the test set now. So you can see this test set didn't change much. Well, obviously, we didn't train on this. Here we have the system that we finished. Just a couple of days ago, in fact. We actually do a little bit worse on Remedia, and we do 5% better on the CBC training. So we're nowhere near passing, and we can think about exactly why that is, and that's what we'll be doing throughout the rest of the talk. And one thing to notice is that we didn't overtrain. Now, we weren't terribly pleased with these numbers in general, but in many ways it's good, and I'll say why that's a good thing, that this type of approach isn't enough, that you need more information. One thing we looked at is, well, what if we had a system where the teacher told Spot which sentences contain the answer, what the question type was, and marked up the things of those types. So you think, well, that's pretty much everything. But in fact, it isn't. It's because there are numerous things within the right sentence that have the right type. So if you just pick between, if you don't have any features to distinguish between the things in the same sentence that are of the right type, what this is saying is, look, the answer to that when question has, the sentence that contains an answer has a couple of temporal expressions, and you have to pick out which one. And if you don't have features to get at that, and the system, this one didn't, then you're only going to get chance. So if you have 3 things and you have chance, you're in the 30s. Okay. So analysis of the spot cheats run. There's so that's essentially what I just said, 1.78 competing but incorrect candidates in the sentence containing the answer. So you're going to have to get at, this is not an IR task. You can't just do word overlap for the ranking, which is what we were trying to do. You have to get into understanding more of the syntax of the question and things around it. So there's a lot more, it's a lot harder task than the hypothesis that we put forth in this workshop would have it. So analyzing the 4.0 run, why doesn't it get 36%? Why is it in the 20s? Why isn't it able to do as well as the perfect system? We have 17% error rate in the question analysis. Actually, it's a little bit higher. It's 19%, I was just told, in the question analysis. So that percent of the time, you're not assigning the right type. We have the semantic taggers have some problems. We have many more competing candidates than we should because of presumably because of precision problems with these taggers, and we're also not able to identify the proper sentence with this overlap. So we're not getting the sentence that contains the answer very well, and we believe that there are bugs. So we actually, we'd love to have 2 more weeks to make this system what it can be. So what's the punchline? I've gotten at this a little bit. Reading comprehension exams are hard. Even when you know which sentences contain the answer and have other information about which one of these 31 types that we defined the question is looking for, it's still hard. There's lots of distractors. There's lots of competing candidates. We need information that can help Spot make intra-sentential distinctions. And Pranav's going to talk about some of those, and Matsu's going to talk about some of those. Okay. I think. So that is the end of what I have to say. And as I just mentioned, some of these things that this extra information that we need will be talked about. And now what we're going to do is Eric's is going to talk about the evaluation metrics and some more detailed results on Spot.
Okay. So what is the criterion by which we're evaluating our system? What are the numbers that Mark gave earlier? Well, we're taking reading comprehension exams. So what we'd like to say is, how many questions did we get right on a given exam? Well, then what does right mean? So there are 2 notions that we came up with. So this is a question from this polar lander story that Mark showed earlier. For the question, who is the polar lander's project manager? The right answer, based on the passage, is Richard Cook. So the short correct response notion of correctness is just the answer to the question and nothing more. And the goal in requiring this sort of response is to sort of see that the system understands the question and returns just what you need. A different sort of criterion is the second one here, inferable from response. And by inferable, I don't mean logically inferable. What I mean is that if a human was given the text, the response that you're trying to grade, can the human figure out what the answer is? So a human looking at this complete sentence could say, okay, now I know who the spacecraft's project manager is, it's Richard Cook. So this whole sentence counts as a correct answer. So this criterion is based on a different sort of use of the system, using it to answer questions. So all the numbers, if we report a single number, as Mark did before, those are going to be corresponding to the first one. Corresponding. So those 2 things are abstract criteria, things that humans could use to grade a system. But we need to be able to do this automatically on multiple runs, on blind data, and multiple times. So we have to automatically approximate this short correct and inferable from response. So for each question, we get an answer key. Now, this might come, in the case of the CBC tests that are our main thing, the question writers wrote the answer key. And in the case of the remediated data that Marc mentioned, the answer key came along with the tests. In any case, for each question, we need an answer key. And then we compare the system's response to the answer key. So for the short correct, we have this automated RTST metric, which says, do you have enough of the right words and few enough spurious words? And for the inferable from response metric, we have the REC-T metric, which is, does the text have enough right words? And I'll explain those in more detail in just a moment. But I also want to say that it's important to look at, for the REC-T metric, as well as just the number, how many questions does the system's response have enough words? Also, the percentage of words in the system's response that are spurious. Because, of course, if the system returns the entire document as an answer for every question, then it would get basically perfect recall, and that wouldn't be very meaningful. So one other number that we're going to be reporting besides the REC-T and the RTST is the percentage of words in the system's response that are spurious, that are not in the answer key. OK, so to make this a little bit more concrete, there's a lot of stuff in this slide, but this is just making precise what I said before. Take the system's response and the answer key, stem them, and remove stop words. So in this case, we have 4 content words in the question and 2 content words in the answer, and then compare them. So one of the words in the response is in the answer key. So you get 1 out of 2 and a recall of 50%. And 3 of the words in the response are not in the answer key. So you get 3 out of 4 spurious words in the response. So by our REC-T metric, you have oh, yes, good, greater than the threshold of 0.5, or actually just add it. So by the REC-T metric, this sentence scores is correct. But by the RTST metric, the recall is just at 0.5, but the spuriousness is too high. It's above 0.5, so it scores incorrect by the RTST metric. So the idea being that a user could infer this, but this system hasn't quite focused down enough to call it truly correct by the shortest metric. OK. So one immediate thing you want to ask is, do those automatic metrics that I just described actually correlate to the human abstract ones that I talked about earlier? So Marc and Gideon went through one of our runs and scored it by hand using these 2 criteria. And I compared the results to the results of the automatic metrics. So REC-T agreed to inferable 85% for Marc and 90% of the time for Gideon. And RTST agreed to short correct 79 and 84%. Those numbers are a little bit lower than we would really like. But first of all, Marc only agreed with Gideon 87% of the time, although I guess their disagreement was systematic. So presumably the human inter-annotator agreement is an upper bound for the system. The other thing to note is that the thresholds of 0.5 for recall and spuriousness, that is to say the threshold that you must have half the words right and no more than half junk words, were not thought about very hard. So if we played with those thresholds, we could probably agree much more closely to the human judges. And one other thing I wanted to note was that we measured the REC-T metric against results from the TREC 99 question answering evaluation. Basically, there were 38,000 responses which were scored by humans. And we made an answer key and compared the results of doing the REC-T metric to the results of the human, and that agreed 93 to 95% of the time. So depending on if we set a better threshold, we might be able to get higher agreement. But in any case, we think this is high enough that we are going to be reporting REC-T and RTST metrics as the results of our system. OK. So these are the basic results that Marc mentioned before. And again, so all the upper 3 rows are all RTST metrics, approximating the short correct. And the bottom one is as Marc mentioned, 1 over 2.78. So it's the number of, it's an upper bound based on if you had the right sentence and the right candidates and you picked among them randomly. So one nice thing about this architecture of having, so I'm switching gears, I'm talking about results now, is having this confederacy of taggers, and in general, a loose architecture, is that we can ask questions like, what kind of knowledge sources do we need to solve this problem? How did the knowledge that we had help us? And could the knowledge that we had already help us more if it was better? So one sort of thing we can say is, suppose that we didn't have one of the processors, one of the pieces of analysis that we had, how would that affect the performance of our system? So we have an automated coreference algorithm, and we can take it out and see that the performance doesn't change very much. However, there are other questions that I'd like to ask about this. First of all, the automated coreference algorithm that we have isn't particularly good. So a result that we didn't have time to run, but will surely be done by the time that the paper comes around, is automatically tag the data for coreference. Automatically, by human, tag the data for coreference. So have a human go through and, for all the he's and she's, write down the text that they correspond to, and then using that, see if the system performance improves. And that might tell us, if that helped, that we actually need to work more on getting coreference. Another sort of example of the usefulness of a loosely coupled system is that we can swap out parts of the system. So after the question analysis and after all the taggers run, there's a need to combine the information in some way with something that we call a ranker. And we have a couple of different rankers, one of them based on a set of heuristics and one of them based on a probabilistic log linear model. And so we can compare those two results and see that the one performs better on RTST and the other on RECT.
Say more about those tables. I don't know what those numbers are.
Okay, both of the two? Okay. So, absolutely. The first one is a comparison of the two scores that we use. At the end of the system, after all the candidates are produced by the taggers, figuring out which one should be actually returned by the system as the correct answer. So one of them uses a set of heuristics to compare the different candidates and human-created heuristics. And the other one looks at a bunch of features, and we automatically trained it on the training data, a log linear model, to weight the different features in a certain way and use that to rank the candidates.
And 25% and 15% means what?
Means what? That means that 25% of the questions were scored by, 25% of the responses to the questions were scored by the RTST metric as correct, meaning that they had enough right words and few enough spurious words.
And that is our
primary notion of good.
Yeah, that's the primary notion of correct.
And they were correct. So
We did not mark the human. The numbers you gave on the last slide was how often that metric corresponds to human. So we evaluated the evaluation. So Gideon and I scored a run by hand, and then we looked at how often the RTST was correctly guessed what we were going to say, and that's the numbers he showed there.
Then I understood, but I don't understand the table.
So the table is just those numbers. Now we're just going to use the automated. We're just going to use the automated scoring at this point because we don't have enough person power to go.
I don't know if I should be happy that heuristic is 25% and LLM.
So okay,
I mean,
all right. So let me.
should I be happy?
Well,
I don't know.
Yeah.
So okay. The reason to do this sort of comparison is to see which one of the two we actually want to use in a system. And so one problem with this is that this log linear model, I think this version of the model didn't have actually all the features that the heuristic score did. Also, it was trained on trying to achieve better RECT rather than better RTST, so it's not entirely surprising that it had a better RECT score. So a result that we'll have in the final paper is train it on trying to better the RTST metric rather than the RECT metric, and also train it on the same set of features that the heuristic scorer had. And then using those results, compare the two and see whether it's actually beneficial to use this probabilistic model or whether it's beneficial just to set up a set of human heuristics.
Let me see if I understand. I mean, I don't understand it, but let
Okay.
me see. The way I understand it is that the heuristic for
No, RTSD is not a test set. It's a way of saying whether an answer is correct.
Okay, on the way of saying that it's correct. 25% of the time, it said that it's correct.
No. 25% of the time, the system running, I'm sorry, I must have, 25% of the time, the system, using the heuristic ranker, came up with an answer that the RTST metric said was correct. 15% of the time, the system, using the LLM ranker, came up with an answer which the RTST metric said was correct.
I know, but I have no feeling whether that's good or bad.
So I think
No, I don't mean there's 15 rather than 25%.
So
But
I
if
think
it was
that
100%, I'm not sure that I would like it.
Well-
That's what my.
Well, so I mean, the idea is that these numbers are percentage of response correct. So if it's 100%,
Percentage of response correct or percentage of response agreeing with
correct
with
as
the system response?
correct.
correct as determined by this automatic metric, which agrees to humans. So
I see. The automatic metric agrees with humans the way the previous slide said. It
yes,
agrees.
that's right.
These are ways of checking whether the system's response agrees with the answer key.
I know that that's what you're trying to do. I just don't know if I agree.
No, so we're agreeing with a unique response. And this is
So is that if on the previous slide the thing was 100%
Mm-hmm.
rather than 87 or whatever,
Yes.
then I should be happy if this 25 was 100%.
yes.
Yes. Yes.
That's a lot of ifs.
Yes.
Indeed.
We're sort of at the beginning of this reading comprehension task, and so one of the things is we don't have 15 years of trust in the word error rate. I mean,
Yes.
presumably in the start of the speech recognition in the world, they had to go through and have humans say whether or not the word that the speech recognition system spit out actually agreed with the acoustic.
No, it was much easier than what you did.
But no, but
We
you
created those sentences artificially, and
Oh,
then
I see.
somebody read them.
I see.
Okay, so there was no question.
But there's the word error rate is also is a relatively complicated thing. I mean, there's some sort of edit distance involved.
But not at the beginning. At the beginning, it's
Right,
very
right.
simple.
Right. So we're trying to get to a automated metric which we believe in, and worse yet, we're trying to get to having humans be able to score it consistently, and we're not even the humans scoring it consistently. We're not there yet, and we're getting there with direct. So yes, part of the results of this workshop is movement forward on the getting the inner human judgments, agreement up, and also getting a automated metric that predicts, that correlates with the humans quite highly. So that's part of what's being done. Yeah.
Okay.
So I guess I agree with Fred. I'm still not sure whether your confidence is going up or down in the RTSD versus RT metric.
I'm not trying to compare the RTSD and RECT metrics. I'm trying to compare the two rankers used in the system.
But we're giving you all the numbers.
Yeah.
Which maybe we shouldn't have. We should have distilled it down to
Just the art, yeah.
just the correct what we think is the correct answer.
And the co-reference ablation was a no-op, is that it?
Right.
Apparently so.
And there's a couple of reasons why that could be. One could be that the automated co-ref module isn't good enough, and in order to do that, to see if that's true, we need to use mark up perfect co-ref, which we've done, but we don't have the final results there. The other thing is that we might not be making use of the co-ref information in a way that enables us to score, to find the answer more often. There's always the information's buggy, not buggy, is
Incomplete,
is
and also
incomplete,
you're not.
or we're not using it right.
But I assume you were surprised or you wouldn't have run this stuff.
And we were surprised. We thought we would have gotten some win out of the co-rep. But on the other hand, we knew that we didn't have the best co-rep. Because to some extent, to take home this lesson, of this slide is that we can do this kind of comparisons and ablations, and it's more of a research paradigm. With this reading comprehension exams, we can do these kinds of. We're at the point now where we can do these kinds of experiments. That's sort of the.
More than any particular results of them.
Yes. But
Yeah. I'm going to skip this. One other result that I want to give is that we ran the system. So the results on the test data are the ones that have been reported so far. I'm giving here the results on the training data. On the Remedia corpus, which Mark's talked about, which was the corpus of stories that previous work had been done on this, the ACL 99 paper that we authored. And then also, we just acquired another set of exams from Instructional Fair Incorporated, another set of reading comprehension exams for children, and ran the system on those. And the first three rows have fairly similar results, and I don't know why the last row is different. So that is what I have to say.
Okay, so now we're going to go back to, that was the section on the evaluation metrics and the work that we've been doing on trying to figure out what correctness is and how to grade it automatically. And now we're going to go back to the actual SPOT system and how it works. And so Brianne and Mike are going to talk about the question analyzer. Let's see.
So as Mark said, we're going to talk about the question analysis. We're going to tell you how we pull out what type of thing that we think the question is looking for. This is important because if, for example, you have a how much question, it would be useful to know that you're looking for some sort of quantity or some sort of measure. If you have a when question, you're probably looking for a temporal expression. If you have a who question, you're looking for a person, and so on. So we came up with a hierarchy of question types. And what we mean by question type is sort of a coarse semantic category. For example, in the question, when did the mission controllers lose hope of communicating with the lander? The question type of that question is temporal, because it's a when question. It's not more specific, such as a time or a date, because we can't really infer that from the question. Another example, who is the Polar Lander's project manager? In that case, we're looking for a person name. We're looking for a person, but we can also tell we probably want somebody's specific name. And another example, how much did the mission cost? The answer for that one, obviously, is money. So the goal in creating these question types, we came up with 34 of them. It was we wanted to get sort of a small set so that it was tractable, but we wanted them to have three properties. We wanted them to have a high coverage of the data. So for each question, we wanted to be able to map it to one of these types that we came up with. We also wanted it to be inferable or extractable from the question. So if given a question, we want to be able to actually do the processing to map it to a question type. And we also wanted to come up with question types for which we could create taggers to extract these types, phrases of these types from the passage. The reason for doing this is because one way that SPOT goes about answering a question is it'll come up with a question type, it'll tag things, phrases in the passages that have that question type or that have all the question types, and then it'll try to match them together. You'll hear more about matching them together later on. And so a limited number of candidates obviously is good for SPOT because as we've shown, when you have more than one candidate, for example, in the same sentence, then if SPOT chooses randomly among them, it'll get quite a few wrong, and that happens quite often, as Mark showed. So here's our list of question types. It might be difficult to see here, but I've sort of grouped them together by color. These are actually in a hierarchy, but I didn't know how to fit that on a slide. So these blue ones here are all sort of agent types. The green ones are temporal types. These are sort of numbers and measures. These are location expressions and so on. These are types that they're not very well defined, but they can be answered by sentences or longer expressions that are usually longer than a noun phrase. For example, a statement is longer than a noun phrase usually, and an event consists of verb phrases and such. These types are usually answered by noun phrases. For example, what is hypothermia? That one's a definition. And then we also have a couple of question types in which we really haven't analyzed the question well enough to be able to know exactly what it wants. So we call these default VP and default NP, where we don't know anything really more about the question type except that it's probably looking for a noun phrase or it's looking for a verb phrase. And these occur actually a fair amount in the data.
Okay, this is basically how we developed the question types. We inherited our original question analyzer from Gideon Mann at MITRE, and it originally had 18 question types, and it could have achieved a maximum performance of 78% on the training set, which means that if it had performed perfectly, it would have accounted for about 80% of the questions. So obviously, 20% of the questions it had no way to deal with. And in reality, it achieved about 60% performance. So how did we develop the new question types? We manually examined the training questions. We just slogged through the data, looked at the questions, and tried to figure out what we thought they were asking for. Keeping in mind the three goals: high coverage, extractability from question, and extractability from the passage. And in conclusion, there we go. So with all of our new question types, we could achieve a potential of 100% coverage on the training set and 99.8 coverage on the test set. So there was only one question that we still didn't have a type for in the end. And but like we said, a lot of those are default NPs and default VPs, which we don't feel like we've really analyzed well enough yet, because the number of them is just too large, and there are just too many candidates in the passage. So it's not really an effective way to deal with those kinds of questions. And but if you take those out, we still achieve about 83.7% on the training set and 85.1% coverage on the test set. And this is the distribution of our question types. What we really want you to take away from this is that they're pretty well distributed. There's a pretty even, these numbers are all pretty much the same. And also, there's a good correspondence between the distribution on the training data and the test data. So we don't think we really overtrained to the training data.
So here's some examples of exactly how a question analyzer works. It's implemented in Perl, so we use regular expressions just to capture some patterns, so that just simple matching patterns, basically. And we actually also use some semantic information. We have, for example, a list of person description words like manager and player and singer, those kinds of things. And we have a list of organization words and such. So, for example, some of the patterns are very simple. So, for example, if you see a when question, it's looking for a temporal expression, unless you can type it more specifically with a time or a date. If you see a where question, then it's looking for a location question. For example, where is the Taj Mahal, which is in Atlantic City. Or a what or a which NP question. If you see a what team, for example, then you know that a team is an organization because we have a list of organization words, of which team is one. And so you can then infer that this question is asking for an organization. We also notice that if you see a question that says who is one of these person words, a person description word such as manager, then it's probably asking for a person's name. So if you ask who was the Mars Polar Lander project manager, then it's asking for a specific name of a person, and you don't want to return, for example, manager or the project manager, because that answer will be wrong. And the converse is also true, that if you see a question that says who is and it has a specific person name, then you want to return a person description word. For example, if you see who is Bill Clinton, the answer is not Bill Clinton, unless you want to get into metaphysics. So you want to return a person description word such as the President of the United States. So Brianne talked about how well our question types have coverage of the training and test data. We have 100% coverage of the training data and almost 100% of the test data. And that's sort of an upper bound on how well our question analyzer could do if it were perfect. And this is how well our question analyzer actually does. It achieves 91.9% accuracy on the training set and 80.5% on the test set. And those numbers are the same for recall and precision because our question analyzer returns exactly one type for each question. Some of the numbers that jump out is that recall goes down from the training to the test set on person words, and this person is sort of glommed together of person noun or person description, person name, and person. And the reason that I think that this happens is because our lexicon of person description words such as manager, president, and singer is just limited, and we developed the question analyzer by looking at the training data. And so perhaps we've overfit to the training data in this case. And the same is true of organizations. As you can see, we do extremely well, 97% or almost 98% on the training data, and only 27% on the test data, which is a strong indication that we've overfit in those cases. But in the other cases, our patterns seem to be working relatively well, and the numbers from the training set to the test set go down slightly, but are comparable.
Okay. Yep. So what have we learned? We've learned that for CBC data, the question-answer task is basically doable, and simple patterns can buy pretty good performance. Improvements that need to be made. We've decided that we need more information really to analyze the default NPs and default VPs, and we have a few different options. One idea is to try and subgroup the default NPs by their semantic categories. For instance, if you have a group that is words that food words in your text, and you see the word eat in your question, if you know that you're asking for what do people eat, you can look for food in the text. So I mean, you could group them by semantic categories, which would be pretty labor intensive, I think. And another way to do it would be to analyze the question types using some syntactic categories, such as looking for the trace in the question and then seeing what the governing verb is, and then looking for that verb in the passage. There are a number of different things you could do, some of which Mats will talk about. And the last thing is, you could.
You can also imagine that we created these rules by hand, the patterns that match the questions to the question types. And you can imagine that you can just build an algorithm or a system that would use some machine learning algorithm, pick your favorite one, and just take a whole bunch of training data with questions mapped to correct question types and somehow learn these rules if you give it the correct features. So that's another possibility for improvement. And that's about all that we have to say about the question analyzer. And we'll hand it back over to Mark.
We'll hand it quickly off to the other side. Once you have the types, you then need to see if you can find things of the right type in the passages. And Ellen's going to talk about building things that find these 31 types.
Okay, so Mike and Brianne just told you about how we take every question and we categorize it as to what kind of object it's looking for in the text, which means that we need this confederacy of semantic taggers to then process the text and identify all objects that exist of each type that a question might be looking for. So we have this huge slew of semantic taggers, which we spent a large portion of the workshop either obtaining from other places or developing ourselves. And just to give you one example of what a tagger might do, a pretty simple tagger, in terms of conceptually it's simple, is a location tagger. So we go through the text and we tag every noun phrase that might be referring to a location. So for example, a tourist flocked to Vancouver, we'd highlight Vancouver or mark Vancouver as being a location. And we had a couple different kinds of location taggers to specify what particular kind of location it was. Could be a city, could be a province, could be a country. Actually, a surprising number of the CBC texts talked about planets, so I was forced to create a planet tagger. And a generic location tagger for things like on the beach, near the mountain, expressions like that. So that's just one tagger, but there's actually quite a number of them. This is a list of what I call the object taggers. I'm going to describe a different kind of tagger in a minute. But these taggers here are basically looking for entities that are noun phrases and that generally correspond to concepts that we're pretty familiar with and are pretty well defined. So we have a person tagger, for example, and as I'll explain in more detail in a minute, we actually need two different kinds of person taggers. We need to separate person names, which are proper names that refer to a specific individual like Bill Clinton, and we also need to separate out descriptions describing what their job title might be, or sort of generically what kind of a person they are. So the president, or botanist, or 62-year-old man, those are examples of person descriptions. We also have an organization tagger. So organizations might be things like the United Nations or Johns Hopkins University. We have a temporal tagger, which tags dates and time entities. We have a measure tagger for all sorts of expressions that might be referring to measures that have units attached to them. We have a generic number tagger for numbers that may not have units attached to them, such as 300 cars were stolen last week. We have a title tagger, which is not the kind of title you're probably thinking about, but a lot of the stories ask for the titles of movies or the titles of books, things like that. They're usually quoted expressions. So we have a title tagger that does nothing but identify sort of quoted expressions that are suspected to be titles of movies or books. We have another tagger, which is more or less sort of a back-off tagger that just identifies proper names that haven't been tagged as something else before. So the Declaration of Independence or the Smithsonian Museum would be examples of proper names that are not people or not locations, for example. And then finally, we just have a noun phrase tagger that identifies all noun phrases in the text. That's really just used for the cases where we have no idea what to look for, so every noun phrase goes in the pool as a candidate. And most of these taggers we actually got from MITRE. They had built them previously, but there were a few of them that we felt that we need to develop a little bit more for this workshop, and one of them was a person tagger. So we built a brand new person tagger, and the reason was that most existing people named entity taggers are only looking for these proper names, and we felt a very strong need to look for person descriptions as well, such as the president or the botanist. And I wanted to give you some idea of why person tagging is hard. It's actually quite difficult, especially when you need to look for both of these things. One of them is a problem you're all familiar with, out of vocabulary items. You will never have in your dictionary every person name that you might find in a text, so that's a big problem. And when you need to separate out these person descriptions from proper names, it all gets a little trickier as well. So there's some easy cases like Joe Smith. You probably have Joe in your dictionary. You probably have Smith in your dictionary as well. The student is a good description word that you probably have in your dictionary. Things get a little trickier when you have a phrase like Superintendent Willard Jordan. Okay, you may not have any of those words in your dictionary. You don't know whether all three words refer to a proper name, like Tommy Lee Jones, whether the whole thing is a description, like school board superintendent might all be capitalized and just be a person description, not a proper name. Or, as in this case, it's actually a combination of the two. Superintendent is the description, Willard Jordan is the proper name. And then, of course, you get ambiguity problems as well. Our system for a while was tagging Michael Jordan as a location because Jordan was in our location lexicon. So all of these issues come into play. And one of the things we did, in addition to beefing up our dictionary, is just develop a couple of very simple bootstrapping heuristics to try to automatically infer when we had a new person name or a new person description that we hadn't known about before. So for example, leader Mao Zedong came up. We had leader in our dictionary as a description word. We didn't have Mao Tse or Tung in our dictionary as person names. But we can look at this noun phrase and notice that we have a capitalization pattern going on, and we know the word leader is a person description. So we can infer that since all the words to the right of it are capitalized, that's probably a proper name. Okay, and then we actually do a second pass over the document to find all occurrences of Mao Zedong and label them as people as well. And that's important because the way our system is set up, we first identify the sentence where we think the answer is contained, and then we look in there for something of the right type. So if we had Mao Zedong labeled as a person in sentence 1, that's not going to help us if we're trying to extract something from sentence 8. We need to make sure all occurrences of him are marked up. There are a couple of more heuristics in there. I'm not going to go through them all, but you can sort of get a feel for it. Herpetologist George Yashin. Sometimes we'll have the first name in our dictionary. George is a common first name. We can use the capitalization patterns to infer that herpetologist is probably a description word, Yashin is probably his last name. Do a second pass over the text, looking for noun phrases that might just refer to him as the herpetologist or Mr. Yashin. Let's see. Buzz President Art Engleton is another good example where we have president as a description word, and sometimes that can help us break up noun phrases that are entirely capitalized. We could, for example, assume that everything to the left of president is the description part, everything to the right is a proper name. That's a little bit more risky, but it turned out to work fairly well in the CBC data, we think. So that's our slightly more complicated person tagger. But what I really want to talk about is some of the other taggers that we developed during this workshop.
Excuse me, on the person tagger,
Yeah.
is that done by hand or is that done by some, I don't know, self-organizing principle?
It's done with a small number of heuristic rules. There are about 5 heuristic rules.
So it's if this, then blah, blah, blah.
Yeah.
And the if is filled out by something that you know, it's done
Right.
what I would call by hand.
Yes.
Right. Right. So we created a little pattern that says if you have a noun phrase and you find a description word and everything to the right of it is capitalized, infer all the capitalized words are proper name, everything to the left is a description word, and bootstrap.
And you must have thought whether you could do this, I don't know, in a self-organized way.
Oh, sure. Yeah.
And
Yeah.
and you concluded that that's very difficult.
Um,
Did you even try?
No, actually, we didn't get to that point. We sort of decided we needed this late into the workshop, wanted to see if it was doable, but I think it would be interesting to investigate whether we could do this with more automated methods in the future. Yeah.
Okay, just say, I mean, one of the taggers that we have from MITRE is an HMM tagger that's trained. You use markup text and train it. It's similar to the BBN name entity tagger. So we actually did have a statistical system that learned, but we didn't have the time to mark up all the data in order to try to train that on this corpus for this particular task, which is slightly different from the named entity task for which it was trained. The other thing is Mats actually did look at building, and he's not going to have some time to talk about that, we can talk about it afterwards, learning person and thing descriptions by using a context-free grammar and then saying, look, all the he's, pronouns, that he, anything that's he, that's the area, learn that that's an area where persons are seen, and then assign words that are seen in that same area, and then train it so it's supervised in the sense that you know the pronouns, and then you run it with EM on supervised text, and then it actually does learn quite well all the different things that are persons and all the different things that are things. And so we did some preliminary stuff there. It actually didn't make it into the talk, but yeah, we did work on that.
What surprised me is your statement that this occurred to you late in the project. I would have thought this would be something you would want right from the beginning.
Well, we had a person tagger in from the very beginning. What we realized late into the project is that we needed this distinction between the person descriptions and the proper names. We thought it would be okay to output astronaut Neil Armstrong as the answer, and then we realized that no, it would really help us if we split them. And the person tagger we had been using before, the one that Mark mentioned, was only looking at proper names. It wasn't trying to identify descriptions. So. Okay, so those are the taggers that probably look like things you've seen before. But there are a fair number of questions that are looking for answers that really aren't noun phrases. They aren't sort of well-defined entities in the same sense. So there are things like why questions, which are looking for explanations. So for example, why did the National Arts Center raise ticket prices? Well, the answer is because of a lack of funds. Okay. How questions. How did something happen? How did Vetri save his house? Well, the answer is by soaking it with water. And a lot of what questions, too, are looking for things like definitions and statements and these long strings that correspond to often a huge portion of a sentence that's not just a restricted noun phrase or a restricted verb phrase. And so we decided to think about whether there's any way to try to automatically recognize these other more complicated types. And my hypothesis was that there were some of these types that might be identifiable using lexicosyntactic patterns. Okay, not all of them, but maybe we could identify some of them. And that looks like a fairly promising avenue, although we've only begun to investigate it. But we developed a bunch of what I call explanation patterns, and these patterns are designed to look for possible answers to why questions. Okay? And I should emphasize that all these patterns do use a parser. We use the Sundance parser developed at the University of Utah. So it's not just looking for a string of words or a plain old regular expression. It is looking for noun phrases, verb phrases, and certain parts of speech and things like that. But the idea is that certain syntactic constructs point us to certain kinds of expressions. So a sort of simple explanation pattern that probably everyone would think of is looking for the word because. Okay, if you have a whole expression beginning with because, that's a likely answer to a why question. Because of a noun phrase is another such pattern. Saying turned out to be a pretty good pattern. There are a fair number of keywords that kind of point you to substantial portions of sentences that might be interesting. And so is another good one that illustrates why you need natural language processing, because you can't just look for any occurrence of the word so. If it's an adverb or an adjective, you don't care. You only need to look for occurrences of it when it's a coordinating conjunction. So these are sort of some of the obvious patterns. And there's a whole bunch of additional patterns that look for patterns that use the word meant or means. And there's some other patterns that are a little bit different. So if you see the prepositional phrase with the preposition for followed by a gerund, that is often an explanation for something. So why was he sentenced to house arrest? For growing marijuana. And that was a fairly regular pattern that we noticed, as well as some other sort of co-reference things like that is why. The whole previous sentence points you to an explanation for something. So there, the previous sentence points you to something. And then this last one is one of the most interesting ones, infinitives. Infinitives often are explanations for things, but not always. So first I just put in this generic identify all infinitive verb phrase pattern, and it was over-generating like crazy. And then I started to notice that if I constrained it to only pull out infinitives that are not immediately preceded by a verb or a base or some other sort of non-base verb phrase, then it was doing much better. Okay, so this was really ad hoc, but it allowed me to really get into the data. And I kind of noticed that what you're really looking for are infinitive verb phrases that are not part of a subcategorization frame. Okay, so try to, want to, hope to. Those infinitives are not functioning as explanations. Pretty much all others are. Okay, so this is an example where we just played around with a bunch of patterns, but I think I at least came away with the lesson that if we had a large list of subcategorization frames, which is a future avenue for machine learning types of research, then we might be able to do quite a good job of identifying infinitive expressions that are possible explanations for why questions. Just very briefly, also just found one rule that worked very well for how questions that has sort of a similar feel to it. If you look for prepositional phrases with a preposition by followed by a gerund, it's often the answer to a how question. This was a very, very regular pattern in the data. So how does YNN make a profit? By selling advertising space. And a variety of different statement patterns as well. Looking at gerunds again were really important because they sort of point you to verb phrases and actions that are happening. Condemned, described, suggested, called. There are undoubtedly a much larger list of words that could point you to statements, and again, that's a future avenue to try to automatically learn these things. But for me, at least, I think it was very interesting because I feel like there's hope for automatically identifying possible answers to some of these more complicated question types using fairly general lexicosyntactic rules that I don't believe will be domain independent. That's the nice thing about it. The lexical part is a little bit iffy, but these syntactic rules are really quite general, and I think really would apply to almost any domain. So that's the end of my tagger portion.
Okay, now Mats is going to talk about syntax, and as we mentioned, we have problems. We have numerous candidates in a given sentence that could be the answer, and thus we need to have some way of distinguishing, and that's one of the things that Mats is going to talk about.
Oh, does this work?
I don't know.
Okay, you've already seen the motivation for this, which is that even if we can zoom in on the right sentence, we know the semantic type of what we're looking at. In the typical case, there are two or three candidates of the right type in the target sentence. This is an example of that. Suppose we're looking for this kind of type we call default NP. Think of that as a concrete object or an abstract object. And the context sentence, the question is, what has been built along the river to hold back high water levels? Question type is default NP. The answer context is a sentence you see there. A federal provincial Fraser River Control Program has rebuilt about 250 kilometers of dikes and so on. The right answer is dikes, but all the colored things there have the right type. There are 5 candidates in that context, and what our system does, the heuristic system, it just takes the first one, so it has 1 chance in 5, and in this case it would fail. The idea, if you look at the question and answer, it's sort of clear what makes dikes a good candidate. Well, dikes is the object of rebuilt, and what we're asking for, the what, is the object of built. If you know that rebuilding entails building, then you've got it. And so this is what we tried to do. We tried to come up with a way of analyzing the question and answer so that we could basically identify the governing verb, or in general, the governing predicate for the candidates, and the idea is to use that to evaluate the candidates, to tell you that dikes is a good candidate in this case. No. Okay, so we implemented an algorithm which we call PF governors. What it does is annotate in the text, it annotates each word with a vector of governors and estimated frequencies. The reason we need a vector is that there's ambiguity in the text. So in the correct structure for that example, dikes is the object of rebuilt, but there's also a crazy incorrect analysis where program is a verb rather than a noun, and dikes is the object of that verb program. So this is the annotation which we're actually going to compute. We have a vector of possible governors and grammatical relations like object or subject, and estimated frequencies for those things. So these estimated frequencies would sum up to 1 over all the possibilities. And the way to get to this vector mathematically is you consider the markup a 0, 1 valued vector, which assigns 1 to the correct to one markup, 0 to all other markups. Take a probabilistic weighting of trees, and then consider that a random variable and compute the expectation of that random variable. Oops, shit.
I'm not sure of this. In other words, there is an uncertainty of analysis to decide what the function of the word dikes is.
So let me restate it. If you take any tree analysis, there's a unique such markup.
Yes.
So this dikes is the object of rebuild, it's the object of program, it's the subject of something like that. So in a single tree analysis, you have a unique markup. But there are all kinds of other possible markups. So for every tree, you have a random vector-valued random variable which assigns 1 to the markup which is dictated by that tree, 0, yeah. Then you scale, that's a probability space, and it's a measure on, it's a random variable defined on a probability space of trees. You just compute the expectation of that random variable.
For that particular sentence.
Okay, it's a conditional expectation, right? So it's right. So, yeah. Okay, so the computation is done in this parse forest data structure. So we think of this as a headed product sum circuit which represents all the trees. So you've got some gates in here. They represent unions of sets of trees. And you've got product gates which combine trees by a product operation in a certain algebra. And each gate in this circuit represents a set of trees. Think of them as inside trees. And all the computations of interest are done in this data structure. And you can compute in different algebras in this data structure. The trees are, those are a semi-ring of tuples of trees, actually. You can also compute with inside probabilities, and so forth. What we're going to be computing with actually is these vectors of markups. So each gate in the circuit is going to be annotated with one of these vectors.
You use the word inside from the inside-outside algorithm.
Yes, it's exactly the same thing. So you can run the inside-outside algorithm in this data structure. And this is actually, we do that in this algorithm. We run the inside-outside algorithm also. And we used a existing probabilistic grammar for English, which came from a few years ago. And it's a fairly large grammar. It has about 1,500 rules. Some of them hand-built, and some of them are general rules, which are generated automatically.
Do you feel, by the way, that you get a lot of mileage? I mean, obviously, the probability of these trees goes down fairly fast.
Yeah, well,
so if
yeah.
you took the 10 most probable trees, you'd probably get more or less the same answer.
Well, I actually don't know. No, I actually don't think so. Because there are very many analyses. This is a very loose grammar. It's designed to be able to parse every sentence in 100 million words of text. And there are very many analyses per sentence, on the order of 1 million or 1 billion or so. So you just taking the first 10, I think, is quite arbitrary. And there's no problem with computing with all of them. So there's really there's no problem as long as you can compute in the circuit. There's no reason to make any arbitrary choices. Okay, so you heard this already. Each gate represents it's technically a multi-set of tuples of inside trees. The sum operation is union. Product is a product in a certain semi-ring. And first in the algorithm, we run the inside-outside algorithm to compute inside probabilities and estimated frequencies. And then working from the source, we're going to label each gate with this governor's vector. And this is the core of the algorithm. I won't go through it in detail, but there are certain operations with these vectors which also use the inside probabilities. So for instance, step 10 says if you got a sum gate for each input in the circuit, you increment the vector value of the input by the vector value of the parent gate by that vector scaled by the inside probabilities for the input and the gate. And the other things are also in this same algebra. Okay, we designed and implemented this algorithm in this workshop. It's implemented as new functionality in a parsing and estimation system called LOPAR. The implementation was done by Helmut Schmid, who was visiting here for a week in the context of the workshop. What's new in this algorithm, I think, is this. Oh, I forgot to say that. In that circuit representation, some of the lines were red and some were blue. That represents this head relation. So it's not just a product sum circuit, it's a headed product sum circuit. So for every product gate, one of the inputs is distinguished as the head input, and the algorithm uses the distinction between heads and non-heads. Something else, so that's different from what you usually see, and something else which is a bit different is this computation in the vector space rather than in a semi-ring or field. We've incorporated this markup algorithm into the spot, so we're getting the markups into the pipe, but we haven't run any experiments, and we actually don't have the feature component which would be used by the log linear model or one of the rankers into the system yet. Okay, something else we did was to, starting with this grammar we had, build a specialized question grammar. Basically, we need the same features coming out of the question as out of the text. And we added, so that describes the grammar we started with. It's an existing lexicalized PCFG for English. It has about 800 hand-built linguistic rules and about 900 phrase bigram rules, which give you the robustness, so you can parse almost anything. It's a language model which was trained on 60 million words of the British national corpus, and it includes a bilexical language, bilexical parameters, word pair parameters which are threaded through the head relations in the syntax. What we added for the workshop was, there's no coverage of questions in that grammar at all, except in the robustness component. We added 183 specific rules designed to deal with questions. And what we were aiming for was trying to find the syntactic context for the questioned element in the question. And we use these things called slash categories. It's a standard method from computational linguistics to deal with the WH movement. So basically, when you see slash W there, that means the V base there is a phrase from which the question element comes, or as you call that the trace location in the tree. It's a standard way of putting WH movement into a context-free grammar. Here's an example. So what has South Queens Junior High done with its blah, blah, blah? The fact that you see VN/W there, that means that the trace position, the question position, is inside the verb phrase. And by following down a chain of such slash W's there, that locates the grammatical role of the questioned element. Okay.
Could you put it back on?
Sure.
Sort of small, so it's hard for me to.
Yeah, sorry, I had trouble getting this into the. Okay, so.
So, what has I have trouble even reading.
Let me just go through it. So, the what is the object of done here? What has it done? This is what we want to recover from this question. Yeah. This is. Oh. I switched to a different technology here. Thanks. Okay. What? All right. This is the WH phrase. This is done. And there's a primitive way of thinking of syntax, which is that this thing starts somewhere in the tree and then you move it up to the front to form the question. The way that's encoded in a context-free grammar, and this observation goes back a long time, is that you code that into the context-free grammar by annotating all the phrases. Yeah. So the question element in this case starts out here. Say, it could start down further down in the tree. So you'd code that into the context-free grammar by putting these things called slash categories. And they go from the root of the question down the tree to wherever, in this case, to this level, where the slash category stops, that's where the trace is. That's where the question elements comes out. It's not ordered in the string. You just say, here the slash W's stop, so you call that, if it's an NP, you call that an object role. If there was,
But we don't have any terminals there, right?
Oh, it's just off the screen, so, yeah.
You mean it would be too big?
Yes, it is literally off the screen.
They are not there.
No, the whole tree is there. So we parse the whole tree. Again, it's a robust grammar, so often if there's some junk at the end of the sentence, it just gets parsed by this robustness grammar. And what we're really interested in for the question is just finding where this question word comes from and what the governing verb is, which in this case is done. Okay, so there's a feature. So what we wanted to do was use the old grammar. We need the specialized question grammar because we just didn't have any coverage of questions. But we want to take advantage of that we had this large old grammar which was already trained. And the way we did this was that, well, if we go back to the question tree again, the lower levels of the tree, like this prepositional phrase and everything below it, comes from the old grammar. Same for this noun phrase. So basically, we have the superstructure of the tree is the new question rules. At some point, you switch to the old grammar, and this makes it possible to merge frequencies from the two models. So you can actually re-estimate the model on a corpus of questions and then splice it together, taking frequencies from the old model. And however, we experimented with this. However, our question corpus was so small. We only had 600 questions and so on. And it didn't seem that re-estimating on that really helped.
I'm
Yeah.
not sure. What is the old grammar?
So the old grammar is this thing which was which had frequencies, including lexicalized frequencies, trained on 60 million words. So we thought this has a lot of information, say, on what a noun phrase should look like.
Right.
We need to add something new to deal with what questions look like, but yes, which is this. But we want to keep that information about exactly what makes a good noun phrase. We want to splice those two together to get a better model to use for parsing questions. And so we managed to do that. Yeah, the reason that this is possible, so basically we're going to, for all the rules which were in the old grammar, we use frequencies, yeah, which were estimated from the 60 million word corpus. And the idea was to re-estimate the question rules from a question corpus, and then you just combine frequencies from those two. And it makes sense probabilistically, well, I haven't proven this, but because of this partition in the grammar. So in any analysis of a question, old grammar rules dominate, old grammar categories dominate only old grammar categories. That's the idea for splicing. However, when we did this, I don't know, we didn't evaluate it, but it seemed re-estimated didn't help us, and I think it's because the question corpus is so tiny. We need a much larger question corpus. Another thing is that I think we need more parameter tying features in order to get real advantage from combining these grammars. We want to get some information about what the question part of the tree should look like from the large corpus also. Okay, well, that was it. Yeah. Oh, yeah, I already said what the status of this is. It's implemented but not incorporated into the score.
The number that you've shown doesn't include this feature. Okay, so now we're going to talk about the end piece, the candidate ranker. What's this? This is Pranav.
It's quite clever. Okay.
So at this point, we're going to reorient slightly. We've been talking about these syntactic taggers, these semantic taggers, question analysis, and all of these are fairly solipsistic in that they go ahead and tag the passage relatively independently of each other, well, theoretically speaking. And what we get out of this can be thought of in a document as a set of pairs, where each element is a pair of a tag and the context in which you find it, that is, the sentence. We go ahead and we partition it into equivalence classes by coreference. And we call each of these equivalence classes a candidate. So this is what we've all been talking about. And the task of the ranker, obviously, is to choose the best candidate, which is the best set of tags and contexts. Yeah. And the procedure is twofold. We first extract some discriminating features from the candidates and the context in which you find them, and generate a score, and from there get what you hope is the best candidate on top. So a note, something that we sort of assumed implicitly was that the candidates are both constructed and scored independently. It's possible to imagine that you could relativize a candidate score based upon other candidates within the context, say, or something like that. So there are two open questions. The first is, what are the discriminating features? Where do you get at these features to rank on? And then how do you combine them to produce a score? And these are some issues. These are just some of the issues under this. One that we were interested in particular for our research was, can overlap in question type get you far enough? And by now you've gotten the punchline, but I'm going to reiterate it, which is no. And then the second one under that is, what levels of these features are useful or necessary? And the next slide will make clear what I mean by levels. And then under combinations, should we score them separately? And we assume this a priori, but this is also an interesting question for research. And finally, can we train a ranking system? We use both, as Eric said, some lexicographic sorting, and we also tried to train a ranking system, a log linear model. So what might some discriminating features be? And we divided them into three types that I think are fairly robust. The first are non-sentential features, and these are the things that the question analyzer, for instance, produces. Things like, well, how can we constrain the answer irrespective of the context in which you might find it? So we could say, well, we're expecting some kind of temporal answer, something animate, something locative. And so this hierarchy tries to get at that, saying, I'm looking for this type, but let's back off to some other type. So I'm looking for a person, but maybe I also want an agent. So all of those come into the sort of genre of non-sentential features, in particular type features. And then we have intersentential features. Now, Mark mentioned this idea of finding the context, the best context in which to find an answer. And the intersentential features are supposed to distinguish, oh, this area is a real hot area. This is something that we think the answer is probably in. Look in here. And so we have three areas that we sort of were examining. I should say all of these subcategories are only examples, obviously. So we look at overlap, obviously. Overlap of verbs, nouns, proper nouns, all sorts of things. I'll tell you what we used in a minute. Then there are also issues of semantic relatedness. Synonymy is very important for this kind of task. So phrasal relatedness, synonymy of important words, and also proximity to marked areas. As Ellen was saying with her why questions, oftentimes the clue that you get is not in the actual sentence that contains the answer. It might point to a sentence before or after. And then finally, we have these features that we think we need more of, which are these intersentential features to distinguish between candidates within a particular hot sentence. And those also, we have some overlap features. I'll tell you about one in a few minutes, which actually is just overlap between the actual candidate that you have and the question. And I'll explain why that's interesting. Also, things that Mats was talking about that we're hoping to get in soon are syntactic relations. So the one that he's been working on recently is, does the candidate have the same governing verb as the trace of in the question? And obviously synonymy is also going to be very important here, because oftentimes the trace's governing verb changes slightly, but the semantics is pretty much constrained. And also we have some proximity issues. So how far is the candidate from structurally prominent words in the sentence? This is also something that Mats has been working on. So I'm going to first answer a question that has probably been begged from the very beginning, which is, how difficult is this ranking process? And this is this question that we were trying to answer, is how far can overlap in type get you? So we computed the number of competitors on average to an answer in the best sentence. And we determined best sentence in different ways. This is what this table is showing. In the first case, we used our system to determine the best sentence based upon those intersentential features I talked about. In the second one, we had an oracle. We had, in fact, Brianne go through and mark up what the best sentence was for the given question. And finally, at the very end, we went through and went to those oracular sentences and marked all the things of the type that was returned by our typing. And also, I should mention that the last two also use oracle question typing. I somehow forgot to put that on. So the average number of candidates, this includes potentially the correct one in the first one. There are potentially, on average, 9 questions in the best sentence by spot. Now, this is to be taken with a large grain of salt, because we know our taggers aren't very good, and even our hotspotter isn't very good. So it's very likely our hotspot might not even contain our answer, and it might not even be tagged if it were in the answer. But the next two numbers are much more significant. So now we're tagging within the correct sentence, and we see that still we have about 4 candidates to choose from. So we have only actually one intersentential feature right now, which is fairly good considering its simplicity. But assuming we didn't have anything, we'd pick 25% of the time the correct answer. And then finally, if you go to the best sentence and you tag perfectly, the average number of candidates is about 2.7. And I should say this also assumes like perfect co-reference. So this is really a sort of unrealistic bound. So it could go up or down from here depending on what arguments you make. Because, for instance, an oracular tagger could tag all sorts of noun phrases that sort of moderately good tagger might not. It might tag noun phrases within noun phrases and things like that that could confound the issue. But in general, this number is an upper bound. So I should also mention that these numbers change depending on the type, obviously. So I have some numbers here. Well, some things that are sort of prolific tags are default NP, this big gigantic bag that we have, obviously. But let's leave that aside. Things like agent and location are relatively prolific. They have about 2 to 3 candidates per oracular sentence on average. Whereas there are things that are relatively sparse, like temporal expressions and person names, which is somewhat surprising. So if you're looking for a name and you get to the right sentence, more often than not, you can just find it if you pick it out if your tagging is perfect, which is a good thing to know. But also, agent, location, and these default NPs make up the preponderance of our data set. So it's really unclear how much that will give you if you just go for the sparse things. So now, as promised, our feature list. Non-sentential features. We looked at type match, exact type match, subsumption in the hierarchy, and domain similarity. Am I looking for something nominal? Am I looking for something verbal? We also look for intersentential features based on overlaps of verbs, nouns, words, bigrams, proper noun phrases, all sorts of things. And also we looked at proximity to high overlap areas, in particular for why questions. And finally, for intersentential features, we really had only one, and we're hoping to get Motz's in soon. And this was overlap of the candidate with the question. And this is under my 2 interesting features. I call it overlap M. So I'll tell you about it right now. The idea is if you ask a question like, what was the name of Wang Shibo's film, a very bad answer to return is Wang Shibo, unless, well, that's the name of the film. So the idea is you can have this very dumb statement saying, if I have something in my question, and say it's a proper noun in particular, I really don't want to return that proper noun if I'm looking for some kind of entity. And this works surprisingly well in reducing things without any kind of extra syntactic information. Another one that's very interesting is this removing of noun phrases from our bigrams, because they tend to bias our overlap results, let's just say. Because oftentimes, you might, in a text, you might mention the name of a full, say, school, South Bend High School or something like that. And all of that's 4 words. And so you're going to get a bigram count for that. In addition, whenever you mention that, your bigram statistic goes up. And it's sort of artificial because you might mention it as the school or the high school or something like that. And we found that overlap bigram no NNP is much more reliable than overlap bigram period. So as I said, we have Motz's governance features in the pipe. And finally, getting back to how good our features are, that percentage sign should not be there. I went through and I looked at the top ranked candidates according to Spot 4.0, no oracles now. And I said, okay, how many things have the same feature set? That is the same score according to our lexicographic search. And on average, there's 1.87 candidates with the same score as the top ranked sentence. So that means that these are somewhat discriminating. However, it's questionable considering that we might not be in the right sentence, we might not have typed everything correctly. Right now I'm running experiments with oracles to see how good this really is. Okay, so finally I'm going to spend maybe half a minute on ranking strategies. So we use this lexicographic ordering which says, all right, I'm going to give you a specific feature ordering, and I might use some heuristic rules saying order certain question types differently, use some conditions on things. But in general, it specifies a specific ordering which says I trust one module's output more than another, which is a bad thing considering that in general, we're not exactly sure how well our modules might perform in a given context. So we decided to try some kind of less draconian measure and also something that was trained. So we tried using an LLM to train weights. Our training data, we ran through this training/development data, and then we used our rect as Eric already pointed out, for our dependent variable. Right now, we're trying to run it through with this new RT-ST metric. So the successes, the good things from this were that it learned the importance of type, it gave overlap M a negative weight, saying disprefer things where the overlap between the candidate and the question is high, which is what we wanted. And it also pointed out, wait, if I have 2 verbs in my sentence and I have 2 verbs in my question and they're the same, there's a very good likelihood that that's the right region, which I think is pretty obvious, but that was good anyway. And some other observations we took away from this were that type features, the importance of a type feature is dependent on the type that you're looking for. And we knew this, but we didn't know how important it was. So the problem was we were just running through with all the types and training on all of them. And for some of them, type might be very important. Type match might be very important. But for others, it might not even matter. So let me give you a concrete example. Ellen's Y tagger was supposed to be high precision, low recall. So it says, all right, if I'm in the proximate area and I'm an explanation, prefer me. But it doesn't mean in general prefer explanations, because it's very hard to find these categories. It turns out when we were just returning best sentences, we were getting more explanations than if we were preferring explanations always. So type features are not very useful for explanation questions. And the problem with this is that it affects our training data in total. So if we split the data, it will probably, we hope, we're currently training these things, learn that type is not very important for explanations, but it is for certain other things. And finally, the obligatory slide on comparative results. So I'm quite happy that with our sort of naive feature set, the rect is substantially larger than with this radix/lexicographic search. But the RTST is lower. Why is it? So why is it doing better or worse, depending on the metric you choose? Well, it returns sentences 35% of the time, which isn't surprising. The dependent variable it has says, give me something with the best overlap. Well, sure, if you return the best sentence, you're going to do better than if you choose some minor segment in the sentence, which means that that metric is not the best we could use for this particular task. And it also returned, and 65% of its correct answers were sentences. So that sort of matches our intuitions. And finally, we have some plans to add these extra sentential features, divide the training data by type, and look at synonymy, at least verbal, which will help with our intersentential features. So that's where we're hoping to go with the ranking process. And I have to acknowledge the developers of the LLM system at MITRE, Warren Greif and Jason Rennie. And that's it.
I wanted to add actually that Misha Voloshin also helped with the development of that system. So I wanted to make sure his name got in there also. Okay, so now for something.
I'm wondering if the situation would be better balanced if we took a coffee break now.
That's fine.
And we would then pay more attention
That's fine.
to Gideon.
Yeah, that's very reasonable. Yeah, no, that's a really good idea. I'm sure Gideon would appreciate that.
So we're going to be back 11:05.
Now we're going to talk about an alternative architecture for doing this problem. Something that can perhaps get around, build in some of these syntactic cues for intra-sentence distinguishing features, among other things. So Gideon's going to present this.
And this is also a proposal for continuing work for this year.
Excuse me. As Mark said, now for something completely different. So we've been talking about this spot architecture, which is a confederacy of these shallow taggers, a question analyzer, all these things going on in parallel distinctly. So one of the consequences is that all these pieces are very loosely coupled. And so that has a lot of big advantages. It's very simple. It's easy to add in a new tagger. It's easy to maintain the separate pieces. And it's relatively easy to debug. You can look at the output of each tagger and debug them each independently. And again, as part of that, you can work independently on all these different features. But there's some consequences. The first is that if you have submodules which have a probabilistic output, it's difficult to integrate this, which has the consequence of you have to make decisions before you'd want to make the decision. So one example is we have our named entity tagger, which is a hidden Markov model. So how do you integrate it in this model? Well, you run over the text, and you construct your lattice, and then you do a Viterbi parse through the lattice, and you get what's the most likely category of each element. So you say, okay, well, this is probably a person, and this is probably a location, and then you just take that and insert that into the text. You don't have a confidence level, you don't have a probability of that segment of the sentence actually being a person. You just have one tag. So you've thrown out a lot of information. You've made the decision that you've correctly identified this as a person. Integrating that probability is a little tricky in this architecture, and it's not very clear how to do that. The other aspect to that is that the interaction of these taggers is very ad hoc. So if we have the word babe, it's a movie, and it's also potentially a nickname, someone's nickname. Whether it gets tagged as a movie or as a nickname in this model really depends on whether you run the person tagger or the title tagger first. And there's no way of kind of having, it's difficult to keep both options in. So the architecture that I'm going to propose is hopefully will overcome some of these difficulties of the current architecture. Oops. So architecture I'm going to propose is a stochastic noisy channel model. Looks like the picture didn't get included properly, and there's no blackboard, so I can't write it. But the idea is that there's a sentence, which is Mark. So the example sentence that would have been here is Mark gave Spot a bone, and that goes to a question, which is what did the man give Spot? And so if you can imagine, there's the top sentence and the bottom sentence, and there are arrows going from one to the other. So for example, the man would go to Mark, Spot goes to Spot, the did give would go to gave, and the what would go a bone would generate what. So there's this transformational process from the answer into the question. And also in this picture would be annotation around the short answer extract. So that's what we really want to return. We want to return a bone. That's what Mark gave Spot, a bone. We don't want to return the whole answer. We want to return the short answer extract and the context. So the marking of the short answer is in these two brackets. And so I'm going to call those combinations the annotated sentence. This is similar to our notion of a candidate and a context. So the candidate is the short answer, and the context is the sentence in which it appears. So why is this beneficial? Why propose this? Well, the first is that now the module interaction is very well defined. It's probabilities. Each module has a probabilistic output, which it then can add on and combine into this large hypothesis. And that has the effect of being able to delay decision making until potentially the very end. So you don't need to decide whether any particular entity is a person or a location or a title or a nickname until you eventually want to figure out the answer at the last step of the model. So that's, in some sense, a pretty big advantage. So how would you use this model if you had one? So you would, first, you'd look at the story. You'd identify all the possible short answers. Then you would create these annotated sentences. It's very easy to do. You just put the sentence, put these angle brackets around it. And then you would rank them using this criteria. So this is the first part of that is kind of this translation from the annotated sentence into the question. And the second part of it is the probability of this annotated sentence. Again, so there are a lot of things which are not very well explained and not very well understood in this slide. And I'm going to go through and say, what are the big questions? How do we kind of, how can we get from this kind of explanation to a more well understood process? And I'm going to do that by answering these research questions. So first, how do you estimate that first probability? Second, how would you integrate extra sentential information? We've identified this as something that would be beneficial for our task, namely in co-reference. How would you integrate that into this model? Because I haven't, so far I've just been talking about annotated sentences. I haven't been talking about regions. The next is, how would you estimate what does the probability of the annotated sentence mean? Remember, that's the sentence with angle brackets indicating what the short answer is. What does it mean to have an estimate of that number? And finally, how would you collect training data? If this is going to be a stochastic model, we're going to need to train all these parameters. How do we collect training data to do that? And also, how do we collect enough training data? So the first question is, how do we estimate that probability? And I'm going to propose that we use a machine translation model, statistical machine translation model. And of course, the best known of those is the IBM model. IBM Model 3 is what is presented here. And in that, there's a notion of an alignment between two sentences. So this is a translation into our paradigm. So we have the probability of the question given the annotated sentence is equal to the sum over all possible alignments. So remember, in the picture that I didn't have, there were those alignment arrows. These are those all possible different sets of alignment arrows between the two sentences. And then for a given alignment, you calculate the probability of that alignment and that question being generated by your annotated sentence. And there are essentially three coefficients in that translation model. There are a few more, but these are the main parameters. So one is what's called the fertility model. That's one word in the source going to multiple words in the target. The next is the translation model. So that's a particular word going to another particular word. So this would be, for example, the WH word going to A and the WH word going to bone. Those would be in the translation model. And the distortion model is a model of movement around the sentence. And I mean, a lot of this work was presented last year in last year's workshop where they did statistical machine translation. So I'm not going to go into any more depth here, but there are a number of references you could look at. But this model may not be the best machine translation model, and there are others available to us. And I think that it's not necessarily the optimal model for this case, because this distortion model really is kind of potentially overkill. There's not as much syntactic rearrangement. And additionally, the movement of the WH word, which is the major syntactic change, presumably, is fairly well structured. So we don't have to account for quite as much variability. So the distortion model is things can move anywhere else, and they're relatively unconstrained. So a more structured model might be better in this case. Additionally, I'm interested in looking at doing phrasal synonymy. So looking at X sold Y to Z and saying that's phrasally synonymous to Z bought Y from X. If we could have some more structure in this model, potentially we'd be able to learn things like that and use them. So more structured models in this case could come from Dai-Kai Wu has done some work on learning grammatical, doing phrasing, parsing in parallel on two different sentences and learning translation models on that. And also Pascal has also done work in learning lexical relationships given bilingual data. So it seems like there's opportunity to take work which has been done in machine translation and use it for this problem. I mean, in some sense, of course, the question is why use machine translation? What's the point? And I think there are a lot of similarities between the task of machine translation and the task of question answering, as I've defined it here. First is there are syntactic changes, which are somewhat well understood and well defined. So in particularly WH movement. Also, there are lexical differences. The lexicons are different in questions and answers. Sentences typically don't have WH words at the beginning of the sentence, or at least it's unusual. And also there are potentially alternative word choices. So you could even see a translation model from an English sentence to an English sentence, and you could say this is a better or a worse translation given on how different the word choices were in those two different sentences. Of course, there are some differences from the translation task to our task. Our task requires that the question, which is the target, be match less one-to-one with the originating source, which is the sentence. So we can drop a lot from the sentence to have a good answer which is being generated. Or to put it the other way around, a good answer for a question can have additional information. Also, we really care most about the WH word alignment. If that alignment isn't right and we don't have the short extract, the correct short answer extract, then to some degree we're not solving this problem. And in machine translation, the quality of the alignment, first of all, isn't directly what you're looking at, and additionally, there's not a need to look at one particular piece of the alignment. Also, one difference is we're not generating answers from the question directly. We don't have a question and trying to generate answers from it. What we have is we have a story, and we have a question on material in that story, and we're trying to essentially align this question with information, with a sentence, with what I'm calling an annotated sentence within that story. So we don't have the same kind of decoding step as people have when they do machine translation, when they're given a English sentence and are trying to generate the French translation. We don't have, our task is different. So the next open question that I want to briefly address is how one would integrate extra-sentential information, specifically co-ref. How would you put that into this model? And so it turns out here's one relatively straightforward way to do it. We have our model, which assumes a co-reference resolved sentence, and we stick on in front of it as input a module which resolves this co-reference. And both of those can presumably, well, one question is, can we train each of those independently? So Eugene Charniak and a bunch of people at Brown have a probabilistic co-reference resolver. It says what's the probability distribution over the antecedents for this particular reference. And so we could take that and stick it in and see the performance. Here's an example of what that might look like. So if our text is flowers make seeds, birds eat them, and our question is what do birds eat, we can see first on the bottom we resolve that, we say what's the probability of that co-reference of them being resolved to seeds, and then we above that we take the probability of what do birds eat given that birds eat seeds. And again, seeds here is the short answer, and that's what those brackets mean around it. This example is due to David Urowski. So another question is, the next open question is how do you estimate the probability of an annotated sentence? And what does that really mean? And the first important question is there a limit to possible short answers within a sentence? If there's no limit to the number of possible short answers within a sentence, that's a big problem. We have potentially, that's a very large set to look over. And so the question is, so one proposal that Bill Byrne made is that let's look at the probability of the annotation and the question given the sentence, and then use a language model to estimate the probability of the sentence. So, for example, we estimate the probability of seeds being the answer given that we estimate the probability of what do birds eat, and birds eat seeds, and seed is the answer given that we know what the sentence originally was. which was that birds eat seeds. And then this introduces the problem of now we have to fit that into maybe we have to change our translation model slightly to accommodate the fact that we're estimating both probability of the question and this annotated answer from the sentence. And exactly how to do that isn't clear. That being said, it seems like a reasonable thing that you might want to do because the type of as we've seen, knowing the type of the question helps you understand helps you restrict the possibility of answers to some degree. And the last question is, how do you generate training data? Again, this is one of my lovely pictures, which didn't get incorporated. In this, you have if we were given a question and the short answer, we could first do an IR query and get a set of sentences which contain the short answer. And then we could filter out those sentences relative to their relationship to the question. So if there is overlap with the question words, we keep that sentence. That's a training, that would be our training example. Otherwise, we throw it out and ignore it. So this relies on us having a source of question and short answers. And I suspect this will be easy to get. One obvious answer is look at Trivial Pursuit questions and scan them in or type them in. And there we have questions, short answers. We're in a good situation. Of course, we have training data from the stories we looked at over this workshop, but that's not a huge amount of data. The other aspect to this is we may need less training data than is traditionally needed in statistical MT, namely because we don't have as much lexical translation. Lexical translation issues aren't as big an issue. So we're not, gave to give. That's a pretty well understood, process. It's a change of tense. And so a lot of lexical changes won't be as important or as difficult to estimate. So what is reasonable to do in 1 year? Or I think is a question which you might be asking. And I think pursuing all of the possible different additions of different information into this model is pretty large domain. There are lots of different pieces of information you could add. There are lots of different structural models you could try. I think in 1 year, I think we could generate some training data, have a corpus of questions and answers to the questions, and that would be annotated answers. I think we could look at off-the-shelf, using some of the off-the-shelf translation models. So IBM Model 3 is one, and see what the performance is. There's been some previous work on using that for doing answer finding, where they identify the best sentence, but they don't identify the short answer, which is, as we've shown, a difficult task. Remember, they're somewhere between 3 different candidates, potential short answers within every sentence. So there's still a lot of complexity getting to the short answer from the right sentence. And that hasn't been addressed. And it would be interesting to see how well an off-the-shelf translation model would do. And also, the next thing I think is definitely there are some things we could look at, some new information. One example is the co-reference, adding co-reference to this translation model. Can we simply add in this probabilistic co-reference module? Another example would be seeing how well adding more structure to this translation module helps, how much that helps. Another example would be how to add in a notion of types into this model. So translation models don't have necessarily a semantic class backoff. We might be able to build that into our model, and we've definitely seen improvements on that in our task, having better type taggers. And so maybe there's a way to integrate those into our noisy channel stochastic model. So finally, I want to mention two people who've done similar work. One is Adam Berger and colleagues at CMU and Just Research, and they've done some statistical work on answer finding, and their work has been concerned with finding the best sentence, not finding this short answer. Also, I should mention they've also experimented with using a latent class model as opposed to a translation model for doing the generation, which is another interesting approach. Also, Chin-Yu Lin, who's at ISI, is also thinking about using this type of framework in the upcoming Trek QA track. I've had some personal communication with him where he's said that that's what he's going to do, but we haven't discussed any of the details. Finally, I'd like to acknowledge some people I've had conversations with in preparation. Of course, the whole reading comp team, and especially Marc Light, also Bill and Pascal, and also David Urowski gave some very helpful comments. And that's it.
Okay, so do we want to have questions for Gideon now and then switch, or do we want to do the whole general?
I think might as well do this general first.
Okay, let me go. So, I had some final words. First thing I would really like to do is to make some acknowledgments for the number of people that helped that weren't with us necessarily all the time. Lynette Hirschman was very instrumental in setting things up and actually in many of the details. And of course, being a MITRE, we worked with her quite a bit on over the years on reading comprehension. Lisa Farrow and Jessica and Beverly, they actually worked on getting the test data for us, constructing the questions. And Tim Bevins is also. John Berger, Gideon Mann, and Jason Rennie supported us with building taggers, working on the log linear code, and as was mentioned, Energy did the first cut at the question an analyzer, and actually we went down to Washington to Reston and met with him, talked about what we were doing. Michael Littman was involved of AT&T was involved in both of the preliminary meetings and helped shape some of the direction. Helmut Schmid helped by coming down and working with Mats on the parser. Karen Kukic of ETS visited and gave a talk about uses for this type of technology from the perspective of people who are trying to construct exams and do a better job of evaluating children's reading level or foreign language learners, speakers of English as a foreign language. Then, of course, there's the crew of technical system administrative people here at Hopkins, and we very like to thank them for all the efforts. And then there's the administrative crew that makes sure the cookies are there, and among many other things. I wanted to thank them, and then finally Fred, William, Bill, and Sanjeev for making this a very satisfying intellectual endeavor in general. Okay. Some contributions. So we have, of course, the results. And I think the primary result was this punchline that I mentioned, that there is this upper bound on how well a system can work if you have types and taggers for those types and a question analyzer. We were surprised to find that there would be so many candidates in the right sentence, pretty much right next to the actual answer. And this was the result, this is the concrete result that I would have taken away, well, be able to take away from this. We have and along the way, we have a much deeper understanding of what makes an answer good and bad, and we've started to operationalize that understanding, and that's what among other things, the discussion that Fred started with Eric on what are these numbers and how confident are you in your automated evaluation. And those are the types of things that I think we've made some steps forward here during the workshop. And again, and we built that into an actual system that does the automated evaluation. We have more evidence that this reading comprehension exam thing is something that's interesting. It's a nice driving force for doing syntax, for example, and building it in. I think one thing that's very nice is you can say, well, you know, everyone's been working at parsing for all these years, and that's certainly true. But there's always a question of, okay, if you're just going to evaluate a parser as a separate entity that just generates parse trees, well, that's an interesting task off to the side, but it's also very interesting to see how you can build that into doing a task that has a more, that's closer to actually something you want to do, and yet something that you can still evaluate without having to do a user study. So I think that Matz's work came out of really this point here that look, this is how you can use the syntactic information. You don't have to get the right parse perfectly, but you do need to get the governor, for example, and you can sum over all possible trees. So there's a number of ways of exactly how do you make use of the syntactic information, and that gets driven very much by trying to answer these questions. And I think that driving force will be useful also for CoRef and a number of other pieces that people in natural language processing work on. So it provides you with a place to stick these pieces in and actually figure out what's the important portion of that performance that makes the reading comprehension task possible, makes your performance go up. We have two new data sets, which we will provide, but this one especially, which will be presented to the community for the use of the community. In other words, there's no restrictions on the copyright restrictions on this. And we have this robust system with a simple modular design, which has been constructed, and we've honed many of the different, there's still some bugs as we mentioned, but this is something also that we hope to, much of it is already open source, and we will make as much as possible so that different people can actually take the system, plug in a new CoRef module, plug in a new ranker, plug in a new entity identifier, and make use of this. And again, this is a contribution of the workshop, that this code will actually be out there. And if nothing else, I mean, Mats will be using it, Ellen will be using it, we will be using it, and I think that ETS has already downloaded it, and so has Eugene Charniak, an earlier version, and Mary Harper at Purdue. And so there's already, people are beginning to take the systems and take these reading comprehension exams. And I think this workshop has moved us that much farther along, building a community of people working on these reading comprehension exams and making it a part of the natural language understanding community. I think that's right. There are some possible direct applications. I think one thing is if you have, you would like to actually help people learn English, if you have them take reading comprehension exams, then, and you can tell them, point out, hey, look, this is the CoRef, this is here are the things that are persons in the text if they missed the answer. So there's a way of having a system help the user read and answer questions about a passage, and this might be something that it's an automatic to-do system. That's what I'm getting at. Do the same thing for reading. You can do question difficulty assessment for test construction. ETS is very interested in this. It costs them a lot of money to estimate how difficult questions are, and some of the tools we've been building can be used for that. And finally, if you hook this thing up to an IR engine, this is not exactly directly, but you should be able to build a question answering system a la Trek. Okay. Future work, continue walking spot up the performance hill. Find distinguishing features for ranking, the intra-sentential ones being very important, improving the taggers, and then of course the alternative that Gideon mentioned. And that's what I have. So now let's open it up.
So Eric spoke about the evaluation metrics that you used, and you also spoke at some point about where several members of your team went and said, tried to see how much agreement you had amongst each other. I was just wondering, how does ETS and other such places evaluate third graders to see how well they're answering questions?
So one thing is that
I think they would love to have short answer exams and be able to do that because it's a much more natural way of questioning a child. But they actually have not felt that the short answer would be something that they could automatically evaluate. So what they've done is they've done multiple choice. And so the way they evaluate multiple choice is they just say whether or not you got the right one the right answer. And there's lots of problems with this. And the way they evaluate, so that's part of the answer. Yeah. And so I think we just wrote, and Lynette did most of the work here, an IEEE article, IEEE Trends and Controversies article on automated grading of children, of humans. So Tom Landauer does automatic grading of essays, and this is, of course, there's a lot of press on this. Is this he has some system that says this essay is a good one, and it's a program that does this. So there's obviously a fair amount of controversy about that, and we have potentially a system here that says we can score short answer exams. You don't have to do this multiple choice stuff if you don't want to. Maybe you do, but if you wanted to do short answer, we could automate the scoring. And so ETS is very interested in actually making use of these types of metrics. Of course, and then if you can do that, even if you don't replace the teacher, if you can give feedback very quickly back to the student, the student gets to, they get the feedback quickly, which if you're a system designer, that's exactly what you want. And if you can think about the child as a system, you can do the development cycle very quickly, which I think is something the educational people are interested in. So yeah.
Yeah, you might want to say a few words about our systematic differences. Well, when we were...
Maybe you want to say a couple.
I want to say a few words about our system. So Eric presented results of the differences between Mark and I when we graded these exams and he compared them. And he said that our rate of agreement was 87%. And it turned out that Mark and I almost systematically disagreed on things which I marked as correct and Mark marked as wrong. And in only, in less than a few percent, that wasn't the case. The case was reversed, and predominantly that was on conjunctions. So when there is a list of things, most of the time I marked that, and spot returned one of those. I marked that as correct, and marked that as incorrect.
I was a very mean teacher. And so, and I guess what we're saying is we actually think that Gideon and I had an agreement of 87%, and we actually think that number could be higher if we went back because it wasn't random. I was grading much harder than Gideon.
And moreover, there was no sort of style book as to how they were supposed to grade. They were just given these, basically just the two phrases that I gave in that first slide. So if we had if we had a sort of little training session as to how you're supposed to grade, then we could usually get a much higher rate of grading.
But presumably this is why one reason, teachers worry about being consistent among students, but of course they should also, it'd be interesting to know the inter-teacher reliability scores.
So considering the questions you disagreed on were the difficult ones, did you try to see what the performance would be on the ones you agreed?
I'm not sure that's... First, I'm not sure necessarily they were the difficult ones. But no, we didn't. That would be a good thing to do.
Well, I suppose multiple choice questions are not of any interest in real life, except for testing students. But I wonder how well you would do if the multiple choice, if the choice was there, because at least it could locate the sentences.
Yeah.
And also the second problem, even if you have the right sentence, you don't know which one of the possible things are the answer, then the multiple choice may very well zero in on one of them and the others are not mentioned in the multiple choice.
So I'm sure Lynette will. We actually considered taking the TOEFL exam, and we worked quite hard with ETS to get release rights to do that. And we didn't actually. We had hoped to get to that, so a port spot to taking multiple choice exams.
Yeah, but that's just to see. But
yeah.
It's of no interest.
Well,
really. After all, you always try to sell it, and I agree with it that this is the first step in an actual extraction of answers to actual questions.
Yeah.
And a human being doesn't have 4 candidates. You know.
Yeah, Mark, can I just say one quick
Of
thing
course.
about the TOEFL test? We actually did spend some time, first of all, we have a corpus of tests. It turns out there's some people interested in semantic and deep inference who want to play with the test, which is fine. It turns out it's very, very hard because, first of all, it's a higher level. I mean, TOEFL tests are students entering college. They're expected to have a good grasp of English. The semantic distance between the candidate answer and the question and the underlying text is much, much bigger than what we're seeing in the test that we've been looking at. There's a lot of inference. There's a lot of synonymy. The answer may be scattered among a number of different sentences you have to put together. So it turns out that it would be very hard to do at that level.
And that's actually one of the things ETS does when they're constructing. They try to make sure that there's a big enough distance between the choices and the question and the actual passage. So.
Can you give us just a rough estimate of what level of performance you would have to achieve by error rate in order for this to be commercially applicable? Is that a fair question?
So I guess we'd have to, so let's say you had email messages and you had a telephone and you wanted to, so this is an application I'm going to describe real quick. Because I wanted
I'm talking about, I really was, it would be easy if you just focused on the application we just talked about.
the foreign language.
ETS.
Yeah, okay.
The very application
Right.
of automatically scoring reading tests, for example. I'm thinking about
I'm sorry, yeah.
people in speech recognition might settle on something like 5% as where the model task performance would have to be before you could convert it to promote. That's all I'm looking for.
Yeah, I think if you're in the 90s, you could use it as something that you would grade children's, get the teacher out of the loop for a daily evaluation. But I think for actually,
You mean where you have repeated measures?
I'm sorry?
Where you have repeated measures?
Exactly, where the idea was for the student to get a lot of feedback so that they could do better. So you'd have like this tutoring system that you give to people who are going to take the TOEFL exam, and the TOEFL exam becomes a short answer exam, let's say, or practice for short answer, and you just want students to be able to take a lot of exams and get feedback quickly, short answer exams. I think in the 90s would be fine for that. But if you actually wanted to do it for the final grading that decides whether or not they go to college, I think you'd have to be presumably in the high. You asked me just for my intuition, the high 90s, but do you have it?
I would say you have to be at least as good as the inter-judge ratings. And even with the E-rater system, what they do is have one human and one system in the loop, and they look at disagreements. So you can say it's sort of half the cost of important tests.
I think we're talking more generally about a question that has been bubbling in my mind since you started talking. You said that one of your goals is to push the state-of-the-art NLP. Here's a good task that shows off many aspects of it. I wonder if now at the end you can deconstruct these aspects. I've noted 4. You talked about processing the question to determine what information to look for, finding the information needed to answer the question, generating the answer, and scoring the answer. And these seem like they're separable tasks in that if you could find information that I could specify in a very clear way, not with a human, but I build into the system what it's looking for, and then you can find it very well. If that part of it's easy, which it looked like it was from your statistics, that you were performing high 80s on those sorts of things, then maybe you can declare success on that, roll that technology out, and go use it. And that's sort of a well-known answer. The name finding is easy. But did you discover any surprising easy parts along the way that you could say, this part, the question analysis, for example, is ready to be rolled out? We're focused sort of on the back end here and saying we wouldn't be interested in answering multiple choice questions, but I have multiple choice questions all the time. Do I turn left or right on my way to hotness?
I do think that the question analysis part is something that could be quite useful. My worries with it is that it would depend. So let's say you rolled it out and said you could hook this up to a website that's trying to answer,
answer questions. And they can make use of a question analyzer, or, that's structured similarly to ours. My question would be, how do the CBC questions differ from the questions that humans actually write when they write at one of these websites? I suspect they might be relatively close, because I doubt that they construct these really long, complex, syntactically complex sentence questions when they're typing at AskJeeves. And actually, we've looked at some of those. We've harvested questions from different sites to take a look at things, and they do look relatively short on average. Under 10 words for a sentence is my memory. But I can actually get that number for you if you'd like. So yeah, I think that's a piece that could conceivably be rolled out and used that way. And what I think would, so that's one answer. And other than that, I'm not sure what other pieces that were easy. Many of the taggers still didn't have. We really focused on getting up to recall, finding everything, but that makes the ranking problem harder. So it's actually interesting to think about what the trade-offs are for when you're looking for answers, as opposed to, say, information extraction, where you just want to find everything, and maybe you're okay with a not such a precision number that's a little lower. So it's actually, the shape of this problem has some different ramifications for what kind of taggers, the way the taggers should be balanced. Too.
I want to go back to this automatic assessment question. So if I understand you right, the whole point was, if people are going to go build a question answering system of some kind, how does one assess them automatically?
Right.
And I think in what you did, you essentially have the question, you have the candidate answer, you have the reference answer.
Yes.
And you're coming up with an automatic scheme of doing it.
Yeah.
And everything, in the two measures that you propose, you only look at the candidate answer and the reference answer.
That's right.
And I have a feeling this is fundamentally flawed, because this is probably okay for a reading comprehension test. But let me give you a make-up example you want to have. Suppose the question was, who gave Spot the bone? Okay, and then the two possible answers were, from one system, Marc Light did it. And in the other system, Marc gave Spot a bone. In both cases, the second answer is worse, because let's say the answer key said Marc Light. But if you think about somebody who's looking for an answer, if I have a huge passage, I haven't read it, and I get back, Marc Light did it, I don't know whether it's right or not.
Yeah.
Whereas if I get back, Marc gave Spot a bone, I know it's the right answer. So I have a feeling whatever automatic scheme you come up with, you have to factor the question in.
Yeah, this gets at I think the way I would rephrase is that your question, and you're absolutely right. And this is called justification. How can you build in to the answer goodness of the answer, the correctness of the answer? We'll call it. It's a good answer if the reader is the reader of the answer, the person receiving the answer, is able to believe the answer. So there's some kind of justification, and that's a part that we haven't looked at. But you're absolutely right. Eric, do you want to say that?
Yeah, because I talked about two criteria. One of them being sort of a user-focused one, and that's what you're talking about. Using it as a question answering system, could a user figure out from the system's response what the correct answer is? Well, no, but I think if you want to know, if you want the system to, if you want to see if the system understood, so you try and find the most concise answer, then I'm not sure that it's as important that it contain that justification.
No, I'm not saying it's important whether what the user is. What I'm saying is this metric is going to say system A is better than system B at answering questions. And your system will come up and say the system that said Marc Light did it is the better system. And what I'm saying is the user will then come and find that he doesn't like system A, he likes system B.
Well, that's what I'm talking about though, is that's a user-centric evaluation. I'm saying that I'm not sure that you always want that is very useful. I'm saying you might also want an evaluation that's not user-centric.
When you say user-centric, you're almost implying that evaluation cannot be done without the user. What I'm saying is, if you factor in what the question asked, and if you change your evaluation metric to take that into account.
I think it's a reason.
Because I don't want to get into questions like what did the user know a priori, what did the user really want. I'm not getting into it at all. I'm saying you have 3 pieces. You want to evaluate the system, and you're using 2 of them, and you're ignoring the third.
I'm just saying that I don't think that the teacher, when she or he grades a student's answer, isn't looking at it as, well, I don't know how they're looking at it, but one of the ways in which I wonder is, I don't think they're looking at it as having an information need and wanting to extract a question. They want to know, did the student understand the answer?
Exactly. So for the reading comprehension task, these might actually be okay because there is an answer.
Okay. Yeah. Okay. Yes.
But
Okay.
other
Yeah.
tasks
Right.
are
For other tasks, absolutely. Okay.
I just wanted to point out that the recall threshold measure, the second measure, is actually getting at what you want. It finds the sort of maximal overlap, and in fact, you could throw the question in there in addition to the answer to get exactly what
That's
you want.
what I'm suggesting.
If you have an automatically trained system, you can simply retrain it to prefer, an automatic ranking system. You could retrain it to prefer those answers.
Right, and I'm just saying that I don't know what the solution is. I'm saying there is something in the question that will help improve these metrics. I just don't know.
That's a good idea.
The example you gave, though, what we tried to do in the evaluation was get at this notion of the short answer, and it's actually a technical term from question semantics. It's called a term answer, and it's distinct from this whole proposition answer. And we tried to come up with an automatic evaluation which gets at that. Now, it could be that you're right. In doing that, we should pay attention to the question also, but I don't think your example shows that, because your example has to do with an mapper or whatever, and I don't think it shows that you need the question to do that. But I bet you're right.
You guys can decide which one to go. Helen, why don't you go ahead?
I wonder if you can comment on your experience and thoughts on how you handle ambiguity at different levels. I mean, you mentioned semantic tagging and question type inference and then parsing. So there's ambiguity at each of those levels that you have to handle, and whether you thought about how to propagate your techniques in handling ambiguity across these levels, so that sometimes when you have a certain ambiguity at one level, whatever evidence you get at another level might help you disambiguate, and how that integrates all together in your system.
So we haven't looked a lot at this issue. We've been primarily trying to make each component as clear as possible. The one ambiguity that exists that hasn't, I don't know if it's come out clearly enough, I want to mention now, is that the answer types, there's a degree of substitutability. So if you're looking for a country, then you certainly can take a location. So there's a hierarchy, and you can go up and down the hierarchy, and so there is some ambiguity there. You know, if you get a point like location, I'm looking for a location. Well, you could be looking for a country or a providence or one of these locative prepositional phrases. So there's some ambiguity there as to which is the best one there, and that. Conceivably, one could build into we have built different levels of tight match between the candidate and the question, and then thrown that into the log linear model and said, here's a bunch of features. This one says it's exactly the same. What the question said and what the tagger says is exactly the same. And here's one that says it's up the hierarchy by 1 or down the hierarchy. And different levels, and then so it gets, one thing I guess I'm saying is the decision is put off until the log linear model. And that's been one way we've dealt with this, is try to be prolific and then hope that your log linear model at the end will be able to save you, because it'll have features for distinguishing between the different ones. And as we've seen, it's kind of problematic. We to some extent, we don't have enough features to distinguish. Now maybe we just, and some of that comes from we need more syntax, we need more understanding of the actual question and sentence in order to have those distinguishing features. So that's one way of putting of phrasing or taking the question you had about ambiguity or uncertainty and building it in. So the idea is leave everything, put all the options in, and at the very end have enough features to discriminate. And I think that there's some flaw there. It'd be better if you had some way of having those modules that made the decisions at the beginning to proliferate, have them somehow be in the loop. And to some extent, that's what Gideon's getting at. There's a way, there's a way of having every module generate a distribution, and then that distribution gets built into a larger generative model, and so therefore you have much more interaction between when you try to pick the probability of the whole thing. It's based on all these different little probabilities, and then you actually also have independence assumptions that you can make explicit. And if you don't want to be explicit, if you don't want an independent assumption, then you can build things together so that you have terms in your final probability formula that actually have the interactions. But right now we're very, very preliminary on any kind of interaction between modules. And you had a question?
Yeah, I had a question on the evaluation of the tagger. You had one figure where you showed the different tags down on the rows, and you showed recall and precision for them. You said you thought you did pretty good because you were getting a mid-high 80s or low 90s on those. Did you take that to be an evaluation of the tag set, or just the evaluation of your tagging program given a tag set?
I believe that one is for the question analysis.
Yeah.
So it's not taggers. So that's looking at the question and saying what the type of the question is. That's not the tag. We didn't show any numbers for how well for example, a tagger that finds person names, how well that's doing at finding person names in the passage. We've tried to get some of those numbers. We didn't feel confident enough with them to put them into the final presentation. They will be in the final report. But so that slide was one that Mike and Brianne presented, and that had to do with how well you could extract the type from the question. Label the question with a type. So is that? So I want to make that. That's one.
Those good numbers you had justify the tag set you're using?
So the tags. I think it justifies the tag set in the sense that yes, we can pull these things out successfully. So that's good. You certainly don't want to have a tag set for which you can't analyze the question and say which one of the tags you're looking for.
But if you collapse the tag set to just 2 tags, default and default.
You'd be very good. Yeah, exactly.
You'd be very good.
So the flip side of that, something that's...
But it's not very informative.
Yeah, exactly. So what you'd really like is to have a tag set that once you know the question type, there is only one thing of that type in the passage, and that would be fantastic. But that's not possible. What you want to get at is if you made your tag set, your set of types bigger, does that reduce the job of the ranker has to do? So we have these numbers about how many candidates are there that you have to weed through that are of the right type in the answer sentence. So we have too many. We have 3 in the right sentence. So with the set that we currently have, so we could try expanding that set, and then maybe the performance we get on the question, getting them out, goes down a little bit, but we go down from 3 candidates on average in a sentence of the right type down to 2. And then I would bet our system performance will probably go up, even though our analysis of the performance of the question analysis goes down a little bit. So you're right. That's sort of you've got these 2 sides. But I also suspect that there's a limit to how you're going to end up having tags like persons with blonde hair who are left-handed and between the ages of 20 and 25. And this kind of type it doesn't really make. I think conceptualizing it as finding a type is somewhat, it's going to lead you astray. And it's better off to think of, you have this type, and that gives you some information, but you need to know that this is a person that's a part of that's doing the answer should be a person who's a part of a giving event, and more specifically gave spot something. And so you have the type, and then you have additional information that you get out of the question that builds in. And I think that'll be a clearer way of thinking about it than coming up with these atomic types. But you're right, there's a flip side.
one measure of that is the number of candidates in the document for that particular tag. So if you had more tags of finer resolution, there would be fewer tags in the document for each tag. So those numbers, I think, start to answer that what you're asking.
Yeah, and I think we're going to focus. That's a very good thing to focus on in the final report, to try to evaluate the set of types, independent from, well, not only, to some extent independent from the actual question analyzer and taggers that we have for it. How good is this type in general? And yeah.
One of the questions I had was services that the performance doesn't seem to depend upon the number of questions that you have, question types, apart from the first part that you're actually finding out the type of question. The question is, how does the performance scale the number of questions types you have?
So you want to. So I think you're asking for the breakdown, like do we do better on who questions and what questions? Yes. Again, these are some numbers that we've been calculating, and there was bugs in the system, and we thought, we're going to put up these numbers, and we're going to say we do really poorly on who questions, but it's because of a minor problem. So we didn't put those. Yes, but we want a breakdown of performance by type. So we do and I think we've done this in our past work. We do relatively well on temporal expressions, and we've had a harder time with why questions, although actually it looks like that might be quite different in this corpus. But yes, you're absolutely right. I wish we had some numbers now, and we certainly hope to have them soon, as to how the system, numbers that we believe in, as to how the performance of Spot performs on the different question types.
No questions. Thank you.
Jason,
Very good.
two more.
Yeah, so just a comment about another possible application. And I'm actually skeptical that the kinds of techniques you've talked about would work for this application, but maybe some variation would. There are a number of services now, websites, Ask.me.com, for example, which try to direct a questioner to the appropriate expert who will be able to answer a question in that domain. So if you think about what it would take to do question answering on the internet, sort of like you have an incredibly long document, which is a concatenation of everything on the web, and you're trying to find the sentence on the web which best answers your question. And the expert finding problem is a simplification of that, because you're not trying to find the sentence, you're just trying to find the subcorpus, namely all the writings of a particular expert, that will have an answer to that, which will contain a sentence which answers that question. Now, the reason I'm skeptical is that I think most of the questions that people ask these sites are of the form, when I try to compile my program, I get the following error message: what should I do? And
right.
There may be many sentences that start out, you should do such and such.
That would be interesting. No, that's a part or a sub piece of question answering that I hadn't thought about. That's interesting.
I had just a short comment on Sanjeev's comment or question, and that is thinking again, and by analogy with the speech recognition technology development program, I think you're probably right to try to keep your evaluation metrics away from user-dependent things. At this stage in development, I'm thinking in terms of resource development, Wall Street Journal stage as opposed to ADA stage. When you have an application-centered R&D program, then I think you need to be very cognizant of user satisfaction and user dependency in your metric. You have to build a metric that has a particular application, user constraints and everything built into it, and then evaluate appropriately. At an earlier stage in technology development, I think to the extent that you can finesse those issues, you're better off making it user independent, even if it is artificial, stilted, and can be criticized as not reflecting the way a real user would use the system.
Well, thank you very much. We resume at 2 sharp.